Today's daily code problem of the day is maximum number of moves in a grid, number 2684. For this problem, we're given a zero-indexed m by n matrix called grid, consisting of only positive integers. We can start at any cell in the first column of the matrix and traverse the grid in the following way. From our position, we can move to any of the cells, either in a row -1, column +1, the same row but column +1, and row +1, column +1. So this means if we start at 5, for example, we could go to row -1, so up, and column +1, so we could go to 4. We could stay at the same row and go to column +1, which is 4, or we could stay in or increase our row by 1 and increase our column by 1 and go to that 4. So we can get into the 3 4s. And we can move into any of these 3 4s such that the value of the cell we move into is strictly bigger than the value of our current cell. So if we start at 5, we cannot traverse anywhere past 5. If we start at 3, we could go from 3 to 4, from 4 to 9, from 9 to 11, and that would be our path. If we start at 2, we could go to 4, from 4 we could go to 9, from 9 we could go to 11. So we're going to be looking for the longest path, but we also need to keep in mind that we need to find a number that is going to be larger than what we're currently on in the next move. So for each possible starting point, we are going to explore all valid paths through the grid, and then we need to keep track of already visited states to avoid redundant calculations. So this problem is a perfect candidate for dynamic programming with a depth-first search. So for each node, say 9, we could keep track of how far we could go from 9. So 9, we could go to 11. That's the longest possible path. From this 4, we could go to 9 to 11. That's the longest possible path. Same for this 4, 4, 9, 11, longest possible path. So we're going to keep track of our longest possible paths. So let's dive into the code. First thing we're going to do is we're going to initiate a variable to keep track of our grid length and our grid columns. And then we'll have a variable to keep track of our moves. So integer m is going to be equal to our grid length. Integer n is going to be equal to our grid of 0.length. We're also going to have our max moves, so int max moves is going to be equal to 0. Now we're going to use memoization. So memoization for this problem is an optimal technique commonly used in dynamic programming to speed up function calls. And it does this by storing the result of an expensive function execution. So if we have a function that calculates something complicated like a Fibonacci sequence, every time we call the function, it recalculates everything from scratch. This repetition wastes time and memory. So when we're making the same calculation multiple times or same path multiple times, memoization is good at storing the results of function calls the first time they're computed. That way, if the function's called again with the same inputs, instead of recalculating, it will just return what is currently stored for that value. So we're going to use this to store our max move from each cell. So int memo is going to be a new integer of m by n. So we're going to use this to store the farthest we could possibly go in each cell. Then we're going to initialize our memo table with -1, meaning it's unvisited. So for int I is equal to 0 as long as I is less than m, I plus, arrays dot fill memo of I with -1. So we're just going to initialize our entire table to equal -1 as it is currently unvisited. Next, we're going to start a depth-first search from each cell in the first column, and we're going to do that to try and find the longest path. So for int I is equal to 0 as long as I is less than m, I increments. So max moves is going to be equal to math.max, the previous max moves, or the depth first search we're going to conduct. We're going to pass it our grid, our index, a 0, and our MIMO table. After this for loop returns, we can return our max moves, as this is going to search from each position in our first column. It's going to use a depth first search to find the longest path that can be made from that position. So, in our depth first search, how are we going to conduct this? We're going to get our grid lengths again, and then we're going to call to our MIMO function. If our MIMO function already has a position for whatever node we're at, so let's say we start at 5 and we go to this 4, we've already calculated for this 4, the longest path it can go is 9, 11, pause. So it's just going to return that instead of doing the full search again, having to search 4, 3, 4, 9, 4, 2, and then 9, 5, 9, 3, 9, 11. It's just going to already know the longest path. So let's go ahead and initiate or build this function. So we're going to have a private integer called depth first search. We're going to receive an integer grid, integer row, integer column, integer grid called MIMO. So if we've already computed our result from our cell, we simply just have to return that already computed result. So if MIMO of row of column is not equal to -1, that means we've changed it, and so we can return our MIMO of row of column. Next, first before we move on, let's initiate a couple variables. So this is simply just going to be our grid length again, so we could copy this chunk of code right here, our grid length, and we're going to just move it down here so we don't have to retype it. So after we check if it's already in our MIMO, we can then solve it because it's not been solved yet. So we're going to have int max steps is equal to 0. This is going to keep track of the max steps we can make from a node. And then we're going to create a list of possible moves that we can make in our table. So we can either go down one row over one column, over one column, or up one row over one column. So we're going to have a 2D integer array called directions. And we can either go -1, 1. We could go 0, 1. Or we could go 1, 1. So -1 would be up and over 1, or we could stay and over 1, or we could go down and over 1. Those are our 3 possible moves. Next, we're going to explore all of our valid moves and check if the new position's within bounds and valid, and if so, we'll add it to our MIMO. So, for our each integer array, direction in directions, we're going to have a new row, which is going to be equal to our row plus direction of 0, and a new column, which is going to be equal to our column plus direction of 1. This is simply just adding whatever we found in our or whatever our direction is to get on a new row, new column. So if we had -1, 1, it would get the position of 4. That's it. Next, we're going to check if the new position is within bounds. So if new row is greater than or equal to 0, and new row is less than or equal to m, and our new column is less than n, and our grid of new row, new column is greater than grid of new row, new column is greater than our grid of row, column. So we're checking, is new row greater than 0, so it's not out of bounds? Is new row less than m, meaning it's not out of bounds? Is new column less than n, meaning it's not out of bounds? as well as checking to make sure that whatever new position we're finding is greater than, strictly greater than our current position. So now that we have figured out what is valid in this sense, we're now going to explore every position recursively. So we're going to have max steps. It's going to be equal to math.max of our current max steps, or 1 plus the depth for search of grid, of new row, of new column with Mimo. So this looks very familiar to our max moves up here, and it is. So this is going to go through all of our initial starting positions, and this is going to go through each step. So we're double using this recursive method to check each column, each row, each step. So after that, after we discover the longest position that can be made from each node recursively, we're going to store that result in our Mimo table. And whatever we store in our Mimo table is going to be what we return, as that is the new max steps. So Mimo of row of column is going to be equal to our max steps, and then we can return max steps. So that's it for our recursive function. To go through it again, so we're going to compute the maximum moves in a given cell, and we return the stored value from the Mimo table. We are going to define 3 valid moves, top right, right, and bottom right, explore all the moves for each valid move. We check if the position is within bounds, and if the cell value is strictly greater than our current cell value, and then if the move is valid, we recursively explore the position and update the max steps value and store the result in our Mimo table. That way, if we ever come across it again, we don't have to recalculate it. So if we run this, passes our test cases, and if we submit it, passes all solutions. So thank you. If you have any questions, let me know. I'll try and answer them as soon as possible. And follow for more daily LeetCode solutions.